Our first lesson is measurements and vectors. So for you to be guided with our discussion, here is the outline. And at the end of this video, you will learn how to distinguish basic quantities from derived quantities and to apply appropriate units to the different physical quantities, to describe accuracy of a measurement by indicating the correct number of significant figures, to convert measurements using the correct conversion factor, and to solve practical problems involving conversion of units and accuracy of measurements. So first, let us have the nature of physics. So physics is a fundamental science that is concerned with the fundamental principles of the universe, and it is the foundation of other physical sciences. The study of physics can be divided into 6 parts. We have classical mechanics, and then thermodynamics, electromagnetism, optics, general relativity, and quantum mechanics. Like any other sciences, physics is an experimental science in which physicists seek patterns that relate the phenomena of nature. The principal objectives of studying physics is to find the limited number of fundamental laws that govern natural phenomena, and to use these laws to develop theories that can predict the results of future experiments, and to express these laws in the language of mathematics. Now, in order to describe natural phenomena, one must make measurement. So, for example, if you want to know the height and weight of a certain person, then we have to measure the height and the weight and compare it with respect to a standard. So, a measurement involves a number and a unit. When we say the thickness of this book is 10, then it has no physical meaning. So both numbers and units are necessary for any meaningful description of a physical observation. And each measurement is associated with a physical quantity. So physical quantities are quantitative description of the physical aspects of a certain phenomenon. And these quantities can be classified as basic or derived. So basic quantities are quantities that are defined by describing how to measure them. And derived quantities are quantities that can be expressed as a mathematical combination of the basic quantities. Physical quantities can also be classified as scalars or vectors. So scalar quantities are physical quantities that are fully described by a magnitude or a numerical value alone, while vector quantities are fully described by both a magnitude and a direction. So here are examples of basic and derived quantities. So in physics, we have 7 basic quantities. We have length, mass, time, temperature, electric current, luminous intensity, and the amount of substance. While derived quantities such as speed, acceleration, volume, density, force, power, and energy are combinations of the basic quantities. Examples of scalar quantities, we have length, mass, time, temperature, speed, energy, and density. So these physical quantities can be completely described by its magnitude only. And we have the vector quantities like velocity, acceleration, momentum, displacement, force, electric field, and weight. To make accurate, reliable measurement, we need units of measurement that do not change and can be duplicated anywhere. So the most commonly used system is the SI or the metric system. In this particular system, the unit of length is meter, the unit of mass is kilogram, the unit of time is second, the unit of electric current is ampere, temperature is given in Kelvin, luminous intensity is given in candela, and the amount of substance, mole. In mechanics, all the physical quantities that we will encounter is based on the three basic quantities: length, mass, and time. Length is simply defined as the distance between 2 points in space. 1 meter, which is the basic unit of length in the SI system of units, is defined to be the distance light travels through a vacuum in exactly 1 over 299,792,458 seconds. Mass is the amount of matter in an object. 1 kilogram is defined as the mass of a particular international prototype made of platinum iridium and kept at the International Bureau of Weights and Measures. It was originally defined as the mass of 1 liter of pure water. 1 second, which is the standard unit of time, is defined in terms of an atomic clock. It is the time taken for 9,192,631,770 oscillations of light emitted by a cesium-133 atom. Note also that aside from the SI system of units, we have the British system and the CGS system. In the British system, length is measured in miles, feet, and inches. Mass is measured in pounds. And in the CGS system, length is measured in centimeter and mass is measured in grams. So here are measurements of length, area, volume, and mass in the metric system and their corresponding British system equivalents. Sometimes we run through very small or very large numbers as we measure. For convenience, we will use scientific notations and prefixes. So here are examples of unit prefixes. Now, in terms of mathematical operations, physical quantities can be added or subtracted only when they have the same units. For example, you can add 5 meters and 3 meters directly, but you cannot add 2 kilometers and 4 meters directly. You must first convert one of the terms into another so that they will bear the same units. Also, terms equated must have the same units in order to be dimensionally correct or consistent. Conversion of units is also done when you want to express units into other systems of units. So for example, if you want to convert measurement from SI or the metric system to British system or vice versa. So here is a list of some conversion factors. So for example, if you want to convert 4.6 miles to feet, we need to use conversion factors. Conversion factors are simply ratios of equal measurements that are expressed in different units. In the previous slide, we have learned that 1 mile equals 1.609 kilometers, and 1 kilometer is equal to 1,000 meters, and 1 meter is equal to 3.281 feet. So take note that the ratios are written in such a way that unwanted units will cancel out. So 4.6 miles is equivalent to 24,283 feet. In the same way, we can also calculate the number of seconds in 2 hours. So this would be the appropriate conversion factors. We have 1 hour equals 60 minutes and 1 minute is equal to 60 seconds. Multiplying 2 hours by these two conversion factors and canceling out the unwanted units, we will obtain 7,200 seconds. In the third example, we are asked to convert 27 grams per centimeter cube to kilogram per meter cube. So this will be the correct conversion factors. So we have 1 kilogram is equivalent to 1,000 grams. And then we have 1 meter is equivalent to 100 centimeter. So writing the ratio in such a way that the unwanted units will cancel out, then we will obtain 27,000 kilograms per meter cube. Uncertainty or error arises in experimental observations. It is the difference between the obtained or experimental data and actual or standard data. The source of error comes from either the instruments used in experimenting or from the observer itself. Determining the number of significant digits or reliable digits in a quantity helps lessen the percentage error. Quantities can also be expressed in scientific notation in order to count the number of significant digits. The rules in counting the number of significant digits or figure are as follows. So the first rule, all non-zero digits are significant. For example, 566 has 3 significant figures and 27 has 2 significant figures. So the next rule, zeros between non-zero digits are significant. For instance, 203 has 3 significant figures and 200,405 has 6 significant figures. The next rule, we have zeros before non-zero digits are not significant. So for example, we have 0.0033 has only 2 significant figures. And this number has 6 significant figures. The fourth rule, we have zeros at the end of a number and to the right of a decimal point are significant. Examples, 22.00 has 4 significant figures. And this number has 7 significant figures. And the last rule, zeros at the end of a number without a decimal point may or may not be significant. So 200 has either 1 or 3 significant figures. There are also rules in expressing final answers when adding or subtracting and multiplying or dividing quantities. In addition or subtraction, the number of significant figure does not matter. What counts is the number of decimal place. The final answer is expressed with the same number of decimal place with the term with the least number of decimal place. So for example, 1.034 meter plus 3.3 meters equals 4.334 meters. However, the final answer should be 4.3 meters. In multiplying or dividing, the final answer is expressed based on the term with the least number of significant digits. So for example, 1.25 meter multiplied by 2.3 meters equals 3.125 meters squared. So the final answer should be 3.1 meters squared. Now let us try to answer this sample problem. So the fastest growing plant on record is a Hesperonychus whippley that grew 3.7 meters in 14 days. What was its growth rate in micrometers per second? So we are given with the length 3.7 meters and the time, which is 14 days. Now growth rate can be obtained by taking the ratio of the length of the plant and the time it takes for it to grow that length. So you have 3.7 meters divided by 14 days, and then multiplied by the correct conversion factor. So we know that 1 meter is equal to 10 to the 6 micrometer, or that is about 1 million micrometers. And then we also note that in one day we have 24 hours, and in 1 hour we have 3,600 seconds. So multiplying this and canceling out the unnecessary units, we will obtain this value. We have 3.1 micrometers per second. So here is a problem that you can work on to test your understanding. A rectangular building lot has a width of 75 feet and a length of 125 feet. Determine the area of this lot in square meters. Okay, the correct answer is 871 square meters, which is given strictly in three significant figures. For your assignment, you have to answer these two problems and submit it through Google Classroom. So see you in the next video.